All right, this is the last part of our Unit 2 notes, tides and ocean currents, and probably the most challenging part of this unit, particularly towards the end. But don't worry, we have days of other activities and review to do before the test. So you will be ready if you do what I give you, okay? So hope you did your bell work. What causes the tides? Are tides the same everywhere in the world? And why do you think this? We are going to explain how tides are produced, how the alignment of the Earth, Moon, and Sun take part in that. What does coastal geomorphology have to do with anything? And the rest of that stuff, how it affects tidal range, okay? So tides obviously are the intervals of water movement, as you're seeing in these pictures, in these animations, on a coastline. So it's where in the littoral zone, remember that word from the last set of notes, and that whole region affected by that change in water. That change in water are tides. And of course, it's caused by the gravitational pull of the moon and the sun. If the moon didn't exist, the sun would still have an effect on the tides, although not as great, because even though it's bigger, it's 93 million miles away, but it still has a tug on us, right? It holds us in orbit. But the moon causes it to be much more drastic, and we'll find out why full moon and new moon are the most drastic times, as opposed to quarter moons, or what you see as a half a moon. We'll talk about that later. So the range is the difference between the highest and the lowest tides between a day. Okay, here's the Bay of Fundy in Canada. They have the largest, greatest tidal range of any place in the world. You can see how great it is at those two locations. All right, so as I said, range is affected by Earth, Moon, and Sun and how they align. These pictures are very important for understanding what I'm talking about here, okay? So if they're in a straight line, you're going to have a pull from both directions, okay? And you get what's called, now this is of course exaggerated for the ease of understanding the diagram, but you're going to have this what's called a tidal bulge. The moon and the sun will be pulling the water on opposite ends, like that. And that would be, of course, a full moon. Full moon, the sun is going to light up the whole face of the moon. So on full moons, you're going to have higher highs and lower lows. If the moon were here, that would be a new moon, and you would have the sun and the moon pulling in the same direction, and you would have higher highs and lower lows as well. So twice a month, you're going to have higher highs and lower lows. But then, when the moon, as it's moving around, so the moon is moving around us, and we are moving around the sun at the same time, the moon is at a right angle, either direction. It's going to be pulling kind of opposite the sun, not opposite, but at a right angle to, and so the tidal bulge will be decreased. And you will have not as high highs and not as low lows. And so this is called a spring tide, very important word. And these are called neap tides. Neap tides. Spring and neap. Now yes, coastal morphology, geomorphology, the shape of the Earth at the coast, coastal geomorphology. These pictures are pretty amazing and funny. So as the coast narrows like this, I've seen this before. I went to Canada when I was 21 years old by myself. Only time I've ever traveled anywhere alone. None of my friends were able to go with me. They were too busy. So I drove from Long Island to New Brunswick. Okay, and I was able to see a tidal bore like this. So as the coast narrows, incoming tide will build up on itself and make a wave. This is a tidal wave. more commonly known as a tidal bore, not a tsunami. Don't confuse these two. And people surf these things, as you can see here. This guy is a local reporter in Canada, in Coriolis. That's, you know, it's I think it's French, but anyway. So he's watching the tidal bore come in, and this looks like he's closer, but he's really not. But he still has to run because it's coming up, and he has to run away from the tide. That's pretty funny. So when I saw it, I was standing on the edge, over like on the side, and watching the tide come in a wave. It's just amazing. If you ever have a chance to see a tidal bore, you should do it. Okay. So other things affect tides: wind, air pressure, size of the body of water. So the more wind, the more it's going to move water. You could do it in a glass of water. You blow, you know, or a bucket of water, and the water, you're going to see the water make waves and blow to one side. Well, imagine the earth wind, right? Blowing on the ocean from a certain direction. And it's going to push that water. It could push it up into a body, an area like a lagoon or in an inlet or something like that, or a gulf or a bay. Or it could push it out. Air pressure, pushing down. How much air pressure, how much air from the surface to space is if it's denser, it's going to push down more, which is going to push that water to another location and affect the tides, either make it higher or lower. And of course, the size of the body of water has an effect on that too. Before that, we go back to air pressure. This is a hurricane where you have a very low air pressure in a hurricane, particularly in the eye, okay? And so the water on the ocean side is going to flow away without raising the sea level much. But the wind-driven side, okay, the water is going to pile up as it's moving this way. Because behind this is lower pressure, and you've got this surge, pressure-driven surge. What kills more people in a hurricane is not the wind, it's the flooding from tidal surges, from the land flooding because of that. And then back to the size of bodies. So larger bodies of water, like oceans, seas, gulfs, they have greater tidal ranges. Small bodies, like a lake, will virtually have no change because it's just not over an expanse of the surface of the earth big enough to make water move from one side to the other. It's a very indiscernible amount. Okay, so the spring and neap tides again. Here we go. So again, spring tide has the largest tidal range, occurs twice a month. So here and here, okay? So when it's in a straight line, it's going to be the largest tidal range. Greatest gravitational pull. Again, full moon, new moon, okay? Spring tides. And then your neap tides here at 90-degree angles, neap 90, they both start with S. Straight, spring, they both start with, N for neap and 90, and then spring and straight both start with S. You understand. Okay, so the neap tides, the 90 degrees, will also be twice a month, but they'll be the least tidal range, the smallest tidal range. And it's also called the first and the third quarter, okay? So here we'll start at new moon, where the moon, you don't see it because the sun's behind it. Here's the first quarter. It looks like you're seeing half, but you're only seeing a quarter of the moon, right? And here's the third quarter, and it looks like you're only seeing half, but you're seeing actually a quarter. So that's why they're called first and third quarter. Okay, so your job, we're going to do an activity on this after this period, not today, but tomorrow maybe, I'm not sure. We're going to be doing interpretation of tidal graphs. And so here's a Boca Raton in Lake Boca Raton. It's not a lake, it's the lagoon in the intertidal zone, in the estuary, behind the Barrier Beach Island. We talked about this in the last set of notes. And so when you look up the tides, you will see charts, you will see graphs like this, charts can be turned into graphs, and you can see that at this date, this time, the tide will be that high, and then go forward in time, and the tide will be this low, high, low, high. And it's very, in this time period, back in whatever year this was taken, which I think was last year, you can see there isn't much change. But in many cases, there are changes. So the low will be here, and the high will only be here. And then the low would be like way down here, and the high would be back up again, all depending upon the moon phases, mainly the moon phases, okay? And this is based upon the lunar phases. You can see that the new moon and full moon would have the highest range, and then the quarter moons, first and third quarter, would be the least changing ranges. And so we're going to see a chart similar to this. And you're going to, so this was September, this was a year ago, okay, when I put this up here. And the dates are here for September with the days of the week, and then how many highs and lows there are every day. Sometimes they're missing some data. And then what time sunrise and sunset and what phase of the moon it is. So this, you can find this all. Go to usharbors.com and you can find all the tides. So going to the beach is why you really need this. If you go fishing, if you have a boat, looking at the tides, there's apps for this. You know, there's actually a tide clock. You can get a clock that, if you set it right, will tell you the tides and how they change, roughly. It'll, just like any other clock, it needs to be reset once in a while, but they're pretty cool. You can get a tide clock. When you go to the beach, you want to make sure you're at the beach during an incoming tide, because you'll have that fresher ocean water. Outgoing tide, like I talked about last time, you're going to have water coming out of the intercoastal, out of the estuary, and it's going to make the water turbid and a little bit less clear. Okay, so that's reasons why you want to understand and know how to use and find a tide chart for your area. Now, of course, if you live in Illinois, you don't care. Okay, if you live in the middle of Texas, you don't care about tides because you're never by the ocean. But people like us who live on the shoreline in Florida and Boca, you care about that. So calculating the tidal range. So these are some things, we're going to do this. Don't do this now, but and you can go back in your notes and do this later when you learn how to do it. But these are some questions you may have on a test. Hint, hint, okay? So calculating the tidal range on September 6th, so you find September 6th, and you find the highest and the lowest for the day, and that would be the range. It's simple. Same thing on the 17th. The name of the tide that will occur on the 22nd, that would be using the moons. Two reasons why the actual tidal range could have differed, so you're going to use things like hurricanes and whatever, wind direction, air pressure, and then why are some data blocks empty, and that's another question we will answer in the future. So, slide 9, we're halfway there. So we're on the same, so we're going to talk about Coriolis effect now, and worldwide ocean currents. So now we're talking about currents, and we're going to talk about surface currents and deep currents, both of them. All right. So currents are that continuous moving ocean water. And these are not tidal. This is different than tides. This is more density related, okay? And temperature related based on density. So that's what we're looking at here. Cold surface waters, warm surface currents, dense, cold, high salinity sinks and forms deep currents. So all of these things are what's driving most of this. Wind does it somewhat, based upon those convection currents in the atmosphere as well. So, but it's all about, mainly about density. Convection currents are made because of density, whether they're in the sky, in the atmosphere, or in the ocean, does not matter. It's all about convection. It's the unequal heating of the Earth's surface by the sun. That's what makes wind. Okay. We're going to talk more about the individual ones soon. All right, so there's questions in the notes about this. So there's a lot going on here, right? I know that, but this is a very interesting picture. Obviously, one of the first things you do when you look at a map is orient yourself, right? Typically, most maps are north, south, west, and east. We spells we across there, just like W-E-D, WED was weathering, erosion, and deposition. There's always ways to remember this thing. So west, east, north, south, right? Florida is where we live right now. We are right there, okay? And so what major current are we affected by? And we're going to say the Gulf Stream. Now that little arrow really should partially also come through the Florida Straits here between Cuba and Florida, because the Gulf of Mexico heats up and moves in this direction. It's going to move upward along the coast, warming this coast. That's why the Florida coast is colder, not Florida, California, don't want to mix those two up. California coast is colder, sorry, go back, okay, because it's getting this North Pacific cold current, and we're getting this tropical or subtropical warm current going up. So that's why right off the coast of South Carolina is a tropical island called Bermuda. And Bermuda is warm, right? Because they're in the middle of the Gulf Stream, all that warm water all year round. Even though it's snowing here, it's still beautiful and tropical in Bermuda. It's the same latitude. It's amazing. And then it gets cold up here and starts to sink back down again. So you can see you've got these clockwise currents in the northern hemisphere, but down here, because it's flipped from cold to warm, to warm to cold, now you're going to have a counterclockwise current. So in the northern hemisphere, all the currents are clockwise. In the southern hemisphere, they're all counterclockwise. Okay. And of course, we're all fans of Finding Nemo, right? And the East Australian current that Nemo and Dory take from the Great Barrier Reef down to Sydney, Australia. They ride the East Australian current. Of course, it's not like that in the movie, but it is a flow of water. All right, upwelling. Upwelling is when you've got this either offshore, could be offshore or perpendicular to the shore, winds. And those winds are going to drive colder, nutrient-rich water up to the surface. Now this nutrients, these are copepods and microscopic organisms that ride this current, are going to feed fish, which in turn feed people. So upwelling is a good natural effect when it happens because the populations explode and there's more food for everybody, the fish and people. Upwelling, okay? Nutrient-rich water from the deep rises to the top because of surface winds. And it usually has to, by steep-sided topography. That's why this doesn't happen everywhere. One of the most famous places it happens is off the western coast of South America, right here. Famous for what we're going to talk about soon. So here's South America, okay? And right along here, you're going to get this, because they have mountains, right? The Andes Mountains, and that run all the way down here from Bolivia and what country is that? Peru, sorry. Peru and Bolivia, they run all the way down the coast. And so this steep-sided topography is going to cause the winds to be greater there, which essentially cause low pressure. And when you cause low pressure, it sucks water up. It's like a straw. You suck on a straw, you're creating low pressure at one end, which pulls water from the bottom of the glass up. The Coriolis effect. I think we've all heard of this, but it is a phenomenon. It is a naturally occurring phenomenon that causes, because of the Earth's rotation, causes large substances like ocean water to move in a circular pattern, okay, or a curved pattern. Does not affect, as many people think, there's a misconception that it makes toilets flow or other water falling through in a small container through a hole to flow in one direction in the South Pole or the Southern Hemisphere and another direction in the Northern Hemisphere. It has nothing to do with the Coriolis effect. It all depends on the shape of the structure the water's in. So we could have toilets. You may have heard toilets drain in clockwise in the Northern Hemisphere and counterclockwise in the Southern. That's not true. That has to do with the shape of the toilet. That's it, okay? All right, so this is currents being deflected because of the Earth's rotation. So what we're seeing here is this red ball is actually traveling in a straight line, but because the Earth is spinning, it looks like its perception is taking a curved path. So the red ball always travels in a straight line, but the track over the spinning globe makes it appear to be in a curved line. So you can see the curvature, okay, appear to loop around the pole, but it doesn't, does it? It's actually traveling in a straight line. But if you were to track that ball over the surface, it makes that pattern. And so this is a little better way to explain it, or a different way to explain it. So the ball is actually traveling in a straight line, but because the Earth is turning, it looks like it's doing a curvature. And that's what is helping to make these patterns of winds across the surface of the planet, is the spinning of the Earth. It's Coriolis effect. The surface currents of the ocean and the atmosphere are deflected to the right in the northern hemisphere and to the left in the southern hemisphere. And then they meet in the middle, and those are called the doldrums, or the horse latitudes, where the winds are very calm. All right. So the formation of global ocean conveyor belt. This is important. You have to label this diagram in your notes. It moves seawater around the Earth. And these are different than the surface currents that I just showed you. Different than the Gulf Stream, different than the East Australia current, and any other currents that you are familiar with or saw on that previous map. So, and this is a problem because this moves heat around the planet. Heat transfer. If this did not happen, our climate could change drastically, like major warming or major cooling, depending upon who you talk, what scientists you talk to, and what information you look at. But there's just so much varying information that it's hard to tell what would exactly happen. But major things will happen, okay, if this ocean conveyor belt is ever disrupted. It's constantly being monitored. There are buoys out in the ocean monitoring these water flows and temperatures constantly. But if this heat transfer were ever disrupted, there'd be major problems. We could have like a very fast cooling period happen also. So not just warming, but cooling. So sinking cold, salty water, dense, right? More dense. So that's going to go deep and travel in this direction, all the way down, and it's going to heat up, okay? Deep current, it's going to heat up at the mix with, it's not going to turn into, but it's going to convert this water here now is going to warm at the equator, right? This is the equator. So this water is going to be warm, and it flows in this direction, mixing here with the Gulf Stream, right? Right there is a Gulf Stream. And together, the warm and the cold ocean conveyor belt systems move that energy around the planet. And I think we're going to try to watch that video, and we'll see what happens.
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths to chart a better understanding of ocean currents. Ocean currents are driven by a range of sources: the wind, the tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis effect. The winds push the ocean beneath them into the same rotating gyres, and because water holds onto heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt, because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow or if it stopped altogether. The only way we'll be able to forecast correctly and prepare accordingly will be to continue to study currents and the powerful forces that shape them. What about the creatures that adapted to survive in these swirling seas? Take a closer look at some truly fascinating
Okay. So, Earth's sleeping giants stirring. So there are 9 tipping elements that are now active. Well, at least that were when I made this last year, this PowerPoint presentation. So, Greenland ice sheet melting, boreal forest decreasing in size, Amazon forest decreasing in size, West Antarctica ice sheet decreasing, shrinking, Arctic sea ice, permafrost all shrinking, coral reefs dying out, and more ice sheets. So all of these things are elements, signals, signs around the world that something could happen to our global circulation that could, and they're related. One is a cause and effect kind of relationship. Some of these are causing, some of these are being caused by. All right, so almost done, a few slides left. El Nino and La Nina is the last thing we're going to talk about. So that means the boy child and the girl child. It's called the boy child El Nino because it usually happens around the time of Christmas and winter. I have a good activity for you guys to carry out after this, after I explain it. But this was one of the most challenging concepts last year for students to get a hold of. So you should really be paying attention right now. So under normal conditions, right? The winds, so this is, the Pacific Ocean, okay? Florida, California, Mexico, Central America, South America, Australia, Indonesia, Japan would be like up there. Okay, so under normal conditions, you can get winds that go from the east to the west, otherwise known as westward, trade winds blowing westward, okay? Surface currents also moving east to west. So that surface water then, because of these flows, will be piling up over here in Australia and Indonesia. And because you've got this flow counter to or away from the shoreline in South America, you're going to get upwelling, good upwelling, which we talked about before. And cold, dry conditions in South America, warm, wet conditions in Australia because of all this moisture and warmth from the tropical area building up over there. Then El Nino arrives. Okay, so here's a comparison between the two. So the winds reverse direction. Now they go from west to east. So this whole kind of thing sinks down, and you've got a reversal of surface currents and wind. So that's going to stop the upwelling. So fisheries, this usually happens. This has a whole year-long effect when this happens. So the fishing is going to go down in South America, okay? Because there's no upwelling, so there's no nutrients, so there's not going to be a lot of fish. Everything flips around. So now you're going to get, because now this flow bringing moisture, now you're going to get warm, wet conditions in South America and cool and dry conditions in Australia and Indonesia. Okay? Vietnam, China, Japan, Russia's up here, okay? So, and that reduces Atlantic hurricane activity because of increased vertical wind shear. So you're going to get less hurricanes during an El Nino. You're going to get warmer winters in North America, in our country. Brings above precipitation to Florida during fall, winter, spring. That's supposed to be our dry season, but it makes it wetter. But it reduces risks of wildfires, but it also increases risks of flooding. So it goes both ways. And increased storminess throughout the U.S. Because of the warmer weather, okay? An El Nino winter. So an El Nino effects around the world, warmer waters, typically less nutrients. We talked about that already. So less phytoplankton, less productivity of food. The warmer water makes zooxanthellae die. We're going to talk more about that in the future. These are symbiotic relationship algae that live in corals that and allow them to get nutrients from photosynthesizing as well as eating. So they die, then the coral gets bleached and the coral dies when you have warmer waters. Cool and dry in Australia, you get more droughts and fires. And then warmer and wet in South America, you get more flooding and landslides, typically mudslides, but specifically. And then La Nina, see here the difference between El Nino and La Nina. This causes the jet stream, which is a high-level winds in the atmosphere, to move northward and weaken over the Pacific Ocean. It's a lot of information, I know, but we're going to talk more about this in the future. During La Nina winters, the South sees warmer and drier conditions than usual, and the North and Canada get wetter and colder. Waters off the Pacific coast are colder, okay, and contain more nutrients than usual. So you've got three conditions: normal, El Nino, and La Nina, and you have to be able to discern between the three of those. So you're going to have to probably go over these notes again, and I have another activity or two activities maybe coming up that will help this also. And that is our notes for this unit.